The alternate segment theorem. This is the most wordy one. Is not necessarily that difficult, but it's probably the hardest one of all the theorems to recognize because they can kind of hide it within lots of other theorems. So we'll look at the proof for this. We'll look at some examples first. So you can see that this is what the theorem kind of looks like. It's a triangle inside a circle, and then there's a tangent. So I can move the points around just like so. So these are all different variations of the position for the alternate segment. I can even move the tangent around. Now, the interactive links that I've put on the document are going to be very useful here. So you should play around with those when you finish this video. Now, here I'm going to show you two angles, and what you're going to see is this angle here, this angle A, stays the same as this angle here. And you can also see is this angle here stays the same as that angle there. So let's look at what this means in terms of circle theorems. So the angle between a chord, so for example, that's a chord, that's also a chord, and that's a chord. So all three sides of the triangle are chords. So the angle between a chord and a tangent, so we're only interested in these two chords now because we want it has to be related to the tangent. So we're not interested in line AB or chord AB. And the angle in the alternate, so the angle between the chord and the tangent is equal to the angle in the alternate segment. So what do we mean by alternate segment? When we say alternate segment, it's a very fancy way of saying the other segment. So let me just break that down a bit further. So when we talk about the alternate segment theorem. So what you can see here is it's just the same diagram as before. So it's just the alternate segment theorem. Now, when we're talking about a segment is something that's split up by a chord. So PB is a chord and AP is also a chord that we're interested in. So we can say that PB separates the circle into two parts. So this part here, the green bit, is a segment, and the white bit here is also a segment. So we're saying the angle between the tangent here and the chord, which is 47, is the same as the angle in the other segment, and that's the shaded in segment, which is the only angle in here that we're interested in is 47. Now we can switch this around as well. We can say, well, this is a tangent and this is also a chord. So the angle between the tangent and the chord here is also the same as the angle in the other segment, which in this case is ABP, so that angle there. A way to recognize this, I'm going to show you now. So let's say this is the diagram that you're given. What you can do is run your finger along the tangent until you meet the point where it touches the circle, and then you can go up the stairs like that. And what that tells you is this is the first angle you come across, so the angle between the chord and the tangent. We'll call that X. When you go up the stairs, then the angle here is also going to be X. We can do the same thing going from the other direction. So you're going along this line here, so following my green pen, and then we're going to go up there. So that means this angle here, we'll call it Y, is going to match this angle in the alternate segment. That might not mean very much yet because you haven't done any practice questions, but I'm going to come back to that hint that I've just shown you now when we do some practice questions. Okay, so now we're going to move on to the proof and see why these angles are the same. And you'll see how it actually relates other proofs that we've already done, just combined together. Maybe a fairly long proof, so pay attention quite carefully to it and slow down or rewind if you need to. So we have a diagram given to us here. It's unlikely that you'll be asked to prove this from scratch. You might be given something like a diagram like this. Now, we can call this angle X, and we can also, again, do the first thing that you always do is draw some radii, and we can say, well, OC and OB are radii. And we can then label this angle, this pink angle here. So we know that if OC is a radii and DE is a tangent, well, then these two angles together have to add up to 90 degrees. So then we can say, well, 90 minus x plus x equals 90. So we know that that relationship is true. Now we know that this OCB is an isosceles triangle. So if that's 90 minus x, well, that angle there must also be 90 minus x. And then this angle here is going to have to be, well, we know angles in a triangle add up to 180. So then this is going to be 180 take away this pink angle and that pink angle. So 180 take away 90 minus x, take away 90 minus x. So when you simplify this down, you can do 180 take away, you you're left with 2x. Now, if you know that this is 2x, again, we're going to use one of the previous theorems, which we don't need to then go and prove that theorem. It's just angle at the center is twice the angle at the circumference. So that means that this angle here, this angle CAB has to be 1x. So that is enough to show that, well, if we started with x there, just because we've decided to call that x, and we know that this is also x, that must mean that the angle BCE is equal to angle BAC, or in other words, the angle in the alternate segment is equal to the angle between the tangent and the chord. That's quite a lot of information to take in. So in order for you to be fluent with this, rather than just moving on, just like previously, pause the video in a minute when I clear the screen, try to reproduce the whole thing from scratch. And you might need a couple of attempts with it. So pause the video now, copy this blank diagram, even though you already have made notes in your books probably, and then have a go at proving this theorem. Okay, so now I'm going to show you the answers again, which I've already shown you. So this is what you should have on your piece of paper that you've just tested yourself with. Two questions to practice. Here they are. Make sure you try both. Pause the video now and then work out X, Y, and Z. Okay, now I'm going to go through these. You really need to make sure you are pausing the video and having a go, because you will struggle with this significantly if you haven't practiced. So for question 1, it's actually deceptively simple, because if you're walking along the tangent and then you're going up the chord, well, that means that this angle here is the same as that angle there. So X is just 62. You can do that straight away. And by the way, you weren't asked to work it out, but again, if you're going up the tangent the other way and then up that chord, well, that means that this angle here has to be 45 degrees, and that's 62, which we just worked out. And then from that, you can actually work out this angle here, because it's angles on a straight line, or also angles on a triangle. Now, the second question, a little bit more required for this one, but still not too tricky. Now, I said that they're quite good at hiding the alternate segment theorem within other questions. This is a good example here. All that they've done is they've added that line there, but it looks like a very different question. So to work out any of the questions here, we know that we have a tangent and a chord there. So that means that this angle here is going to equal that angle there. That's going to be y. We can also say that this triangle is an isosceles, and that's because it's given to us through those two dashes. So that means that this angle here must also be y. So we can work out this angle, these two angles, because we know that 180 take away 50, take away 2y equals 180. I mean, we can just write 50 plus 2y is 180 as well. So 180 minus 50 divided by 2. So y is going to be 65 degrees. So we can label that on there. 65, 65, and 65. Now we want to work out Z. So we know from a previous rule that tangents that meet at a point are at an equal distance. So actually we have another isosceles triangle. So we can just call this X. We can call this X as well. Now to find X, we know that this is just a straight line. So if I just sketch this section out down here, essentially we have 65, 65, and X, and that adds up to 180. So do 180, take away 65, take away 65. So X is 50 degrees, which means that X is also 50 degrees. So let's just tidy that up a little bit. So that's 50, 50. And then we can say Z is going to be 180, take away 100. So Z is going to be 80 degrees. And that is your final circle theorem. Make sure to watch the next video for the instructions, because there's quite specific instructions for this week. All right, I'll see you in the next video.